welcome back. In the last lecture, we were discussing about the Riemann integral and also periodic functions and the integrability of the periodic function. And so, let me today recall one very important properties of Riemann integration, which states that if we have a Riemann integrable function, then it can be approximated by a sequence of continuous function under the integral. So, what I mean by that? Let me put it as a lemma. Let f be a 2 pi periodic Riemann integrable function suppose f is bounded by b, then there exists a sequence of continuous 2 pi periodic functions f k such that supremum over x belongs to minus pi to pi mod of f of x is less or equal to b for all k 1, 2 and minus pi to pi mod of f of x minus of f k of x dx. This goes to 0 as k tends to infinity. Intuitively, what you can see is that in the Riemann integral, suppose wherever your f is, suppose this is minus pi to pi and then you are having certain partition, this depending on the k you choose the partition. So, then the partition essentially now you are basically these are all the step functions what you are trying to take the area of these rectangles like this. So, now instead of choosing this as f k, what you can choose is that you can compromise with very little, like you make this as a continuous function and these f k's are going to do the job. So, that is an sketch of the proof. So, you can finish the proof by yourself. Okay. So, now let us come to our main topic. Till now what we were doing was recalling some of the facts what we have learned earlier and those which are very important for us in this course. Okay. So, let us recall what we did in the first lecture. So, Fourier claimed that if f is a 2 pi periodic function, then there exists sequence a n and b n such that f of x can be written as summation over n equal to 0 to infinity a n cos n x plus summation n equal to 1 to infinity b n sin n x. So, there are several questions one can ask, because first is that what are these a n's and b n's vis-a-vis the given function f. So, Fourier gave a prescription where he claimed that a 0 is equal to 1 by 2 pi integral 0 to 2 pi f of x dx, and a n is equal to 1 by pi 0 to 2 pi f of x cos n x dx, and b n is equal to 1 over pi integral 0 to 2 pi f of x sin n x dx. Okay. So, this is what was the claim of Fourier. Still, it is not clear that given this a n b n, why the series on the right hand side, remember these are all infinite series, why should they converge in the first place? Now, secondly, one can ask, even if it converge, what is the guarantee that right hand side series is going to converge to f of x at every point x? Things are not at all clear. However, this prophetic statement of Fourier is almost true. We will see some of the convergence result in this course, and remember this is a very important questions in for mathematics as well as for the applications. So, what we would like to do is that to find large class of function for which the Fourier series converges, and we must ensure that the convergence it converges to the function f. Okay, so, before computing some of the Fourier coefficients, so let us see observe that f is a 2 pi periodic function. We have the freedom to consider this integral from 0 to pi, or for that matter minus pi to pi, because all these are 2 pi periodic function. F is a 2 pi periodic function, cos and sin a 2 pi periodic function. So, we have the liberty to choose our integral minus pi to pi or 0 to 2 pi. Okay. So, now if f is an odd function, suppose f 2 pi periodic and odd, that means f is, I can consider it as a map from minus pi to r, where f of minus of x is equal to minus of f of x. So, for this kind of function it is enough to define the function on 0 to 2 pi, then it is just the odd one. Now, for this case, let us compute a n, then a n as by the prescription of Fourier. Suppose first a 0, which is 1 by 2 pi minus pi to pi f of x dx. This is equal to 0, because f is an odd function, and a n for n not equal to 0, this is again 1 by pi minus pi to pi f of x cos n x dx. So, recall that f is odd and cos is an even function, therefore, the product is going to be an odd function. So, again this is going to be 0, and for b n, this is equal to 1 by pi minus pi to pi f of x sin x sin n x dx. Now, this is an odd function f, and sine is also an odd function. Therefore, the product is going to be an even function. So, this we can write that 2 by pi 0 to pi f of x sin n x dx. Similarly, we can define it for the even function. Suppose if f is even, two pi periodic and f is even, then what we can get is that in this case, just the calculation like above, we will get f a n is equal to 2 by pi 0 to pi f of x cos n x dx, and b n again f is even, sine is odd, therefore, this is going to be 0. Therefore, for odd function, the Fourier series for the odd function is nothing but a n's are 0. Therefore, this is n equal to 1 to infinity 2 by pi f of x sin n x dx times sin n x. So, this is what, and the Fourier series for even function is summation n equal to 0 to infinity a n cos n x, where a n is given by this formula. So, this is called the cosine series, and that is the sine series. So, now let us compute few examples, their coefficients, Fourier coefficients a n and b n. Now, example first example, the trivial example, let us take f of x is equal to 1. Then a 0 is equal to 1 over 2 pi and minus pi to pi dx, which is equal to 1. It survives only a 0, a 0 it is 1. Now, a n is equal to 1 by pi integral minus pi to pi cos n x dx. Now, if I integrate it, then this is n not equal to 0. So, this is 1 over pi sin n x by n. Now, minus pi to pi if I am taking, then sin n pi is equal to 0. So, this turns out to be 0. Now, you compute with B n, which is equal to 1 by pi minus pi to pi sin n x dx. Now, this is equal to 1 by pi, this one is minus of cos n x by n, and then this is minus pi to pi. So, now this is equal to minus 1 by pi, this is cos n pi minus cos of minus of n pi. Now, cos is an even function. So, this is going to be equal to 0. So, only coefficient for f of x is equal to 1. The Fourier coefficient survives is a 0, and for a n and b n they are equal to 0. Okay. So, now example 2. Now, let f be a 2 pi periodic function, and f of x is defined to be x on 0 to 2 pi. At 2 pi again it is going to take the value 0. So, now let us try to sketch the function. So, this is 2 pi, this is 4 pi, this is minus of 2 pi. So, so 0 to 2 pi f of x is going to look like this, and then 2 pi to 4 pi, this is again going to look like this, and minus 2 pi to open 0, this is going to be look like this, and at 0 this is again 0. So, this is like a concept. Now, if I calculate a 0, then this is equal to 1 by 2 pi, and then 0 to 2 pi x dx. This is trivially is equal to 1 by 2 pi into 4 pi square by 2, which is equal to pi, and a n is equal to 1 by pi 0 to 2 pi x cos n x dx. This is equal to 1 by pi. Obviously, our experience tells that it is x over here. So, let us apply the integration by parts. So, now integration by parts will give me sin n x by n, this is 0 to 2 pi. Remember that n is not equal to 0, therefore, this is minus 1 by pi integral 0 to 2 pi sin n x by n dx. Now, this is sin 2 pi 0, sin 0 0, the first term it goes away. Now, in the second term we are going to get cos n x by n square, again cos is a 2 pi periodic function. So, what we are going to get that value to be 0. Now, B n is equal to 1 by pi 0 to 2 pi x sin n x dx, which is again equal to 1 by pi, by integration by parts is x, then sin integral is cos n x by n with a negative sign. this is 0 to 2 pi, and then this is minus minus plus 1 by n pi integral 0 to 2 pi. This is cos n x dx. So, now here cos 2 pi n is equal to 1, therefore, this is minus 2 pi by n, and x presence of x is 0. So, that is going to be 0, and anyway this integral is going to be 0. So, this is what is our B n. Now, our next example is interesting. Here we are taking f of x is a 2 pi periodic function defined on 0 to 2 pi as x. Now, if I change a little, so this is example 3, that f 2 pi periodic and f of x is equal to x on minus pi to pi. Then unlike the previous example, look at the graph of this function. This is pi, this is 2 pi, this is 3 pi, this is minus pi, minus 2 pi, minus 3 pi, like this. So, now here on minus pi to pi, this is x is going to look like this, and here this is again going to pi to 3 pi, this is going to look like this, and minus 3 pi to minus pi, this is going to look like this. You can see that there is a change of behavior for the f we have defined earlier by giving the value f of x equal to x on 0 to 2 pi, and here I am giving f of x equal to x on minus pi to pi. Now, this is an odd function, therefore, a n is going to be 0. Now, we need to find B n. B n, what we know is that this is 2 by pi 0 to pi x sin n x dx. Now, this we have already computed this. So, for the sake of completion, let us see it again. So, this is x, then with a negative sign, minus cos n x by n is not equal to 0, and then this is 0 to pi, and then minus minus plus 2 by pi, and then this is the integral 0 to pi, x is derivative of x is 1, this is cos n x dx, and then this is n. So, this one is going to be now 2 by pi at this is pi, and then with a negative sign. So, this is minus of pi divided by n, and then cos n x cos n pi is equal to minus 1 to the power n, and 0 x equal to 0 is 0, goes away, and now if I am integrating it, this is sin n x by n. However, it is 0 to pi. So, sin n pi is equal to 0 and sin 0 is equal to 0. So, this gets cancelled. So, this is basically what we have got is that this is minus negative of minus 1 to the power n 2 by n. That is what we have got done. Now, for the fourth example, which we need the similarly, if I take f 2 pi periodic function and defined on 0 to 2 pi to r by f of x is equal to x square, and f is 2 pi periodic. So, as you can see that a 0, this easy computation will give you 2 pi square by 3, and then n not equal to 0, a n from 1 to infinity. So, if you do integration by parts, then the integration by parts you have to, in the first one what you are going to get is that 1 by pi, then this is x square, then this is sin n x by n, this is 0 to 2 pi, that will go away, and then minus 2 by pi n, this is 0 to 2 pi x, then this is sin n x dx. We have computed this integral 0 to 2 pi x sin n x dx earlier. So, this is going to become 4 by n square, and b n, this is equal to, in the similar way if we do that, then this is 4 pi by n. Okay. So far so good. So, for this Fourier has also said that it is not only specific to 2 pi periodic function. We can discuss the Fourier series for L 2L periodic function instead of L is equal to pi. So, Fourier series So, this can be given as summation over n equal to 1 to infinity a n cos n pi x divided by L plus b n sin n pi x by L and plus this is the Fourier series a 0 plus this is the Fourier series. And in the same fashion we can define that a 0 is equal to 1 by 2 L minus L to L f of x dx, a n is equal to 1 by L minus L to L f of x, here cos n pi x by L dx, and b n is equal to 1 by L minus L to L f of x sin n pi x by L of dx. So, that is what the Fourier series for 2L periodic function, and in the next lecture we will see that how we can combine these two Fourier series of 2 pi periodic function. Instead of writing it in terms of cos and sine, we can write it in terms of e to the power I n x, because we know that e to the power I x equal to cos x plus I sin x. Thank you.